Welcome to part 3 and the final part in the Numpy recitation series. So in this we're going to be looking at how we can use Numpy to combine data and perform some basic math operations. So the first one that we are going to see is concatenation, where you essentially join two arrays along an existing axis, and this is valid only if both the arrays have the same shape, except of course in the concatenating dimension. So let's see an example. Suppose you have two arrays of shape 3, 2, 2. If you combine it or concatenate it along axis 0, you will see that the new dimension is 6, 2, 2. And similarly, if you concatenate it along axis 1, it's 3, 4, 2, and along axis 2, it's 3, 2, 4. So it basically increases depending on what axis you're giving it. The next type is called stacking. And what stacking does is it basically joins two arrays and creates a new axis. So let's have a look at how it works. If you have two one-dimensional arrays and you stack it along axis 0, you see that the new stacked array has a dimension of 2, 3. Similarly, if you stack it along axis 1, then you have 3, 2. It basically retains the number of rows and adds 2 columns. And if you add axis is equal to -1, it basically takes the last dimension. In this case, it is 1. So you see the same response in both of these cases. Let's have a look at another example where we use three-dimensional arrays instead. So if both of our arrays have dimensions 3, 4, 5, if we stack it across axis 0, we see that a new dimension is introduced in axis 0 of 2, 3, 4, and 5. So similarly, if you have axis 1, 2, and 3, in those corresponding places, you see a new dimension getting introduced. Let's now look at some common math operations that you can use Numpy for. So the first one is called broadcasting. Let's say you have two arrays, one of shape 1, 3 and one of shape 4, 1. You can actually add these two arrays or multiply these two arrays. And although this seems counterintuitive, Numpy does this thing in the backend called broadcasting, where it does an element-wise comparison and then performs that particular function like addition or multiplication. It basically starts from the last dimension or the rightmost dimension, and it checks if it's the dimension of the two arrays are equal or if one of them is a 1. So let's look at this example. So it looks at 3 and 1 first and sees that one of them is a 1. So what it does is it stretches this or expands this to match the other dimension. So now this becomes a 4 cross 3 array where this is repeated 3 times. Similarly, it then moves left and compares 1 and 4. It sees that one of them is a 1. So this is expanded to the other dimension, which is 4. So this becomes 4 rows and you have 4 cross 3 plus 4 cross 3, and this becomes a valid operation. We can also specifically do element-wise operations. So if you have two arrays of the same shape, 2, 3 in this case, you can add a scalar which will add the same scalar to all the elements. You can add both of these arrays which will do element-wise addition. You can multiply them. Even if you take a square root of this, it will take element-wise square root. Next, let's look at reduction. And in this case, you essentially take an n-dimensional array, apply some function on it, and this will be reduced to one particular number or one particular number per axis. So let's say you have this particular array, which is of shape 2, 3. If you do an np.max, it's going to find the maximum number across all the axes, and in this case, return 0.97. You can also find the maximum value or the minimum value along a particular axis by giving the axis dimension. So you can look through all the functions that we have specified here, go through the documentation and understand in more detail what they do and how they exactly compute these at a reduction level. Finally, you also have comparison in the element-wise operations list. So if you have two arrays of the same shape 2, 3, you can pretty much run any relational operator like greater than, lesser than, not equal to, or equal to, and get the result which says where it is greater than, where it is lesser than, and so on. You can also check using .any or .all whether there exists any element that satisfies a condition, or whether all the elements satisfy a condition, and they will return Boolean values. You can also specify the axis along which you want to test these, and you will correspondingly get results of that particular shape of the axis. Now let us look at some vector and matrix operations, basically matrix multiplications. There are two ways that you can multiply two vectors or matrices. One is by calling np.matmul and the other is by using the at operator. Both of these work the same way. So if you have to do a vector into vector, matrix into vector, matrix into matrix, as long as all your shapes follow the rules of matrix multiplication, all of these are perfectly valid. There is also the dot product that is supported by using np dot, and you can basically perform matrix multiplication using np dot, and this is equivalent to using np.matmul or at for two-dimensional matrices. You can test all of these out in the notebook that's going to be shared with you. Let's now look at tensor dot, which is actually a very important function, especially for homework too. So let's say you have two different arrays, A of shape 3, 4, 5 and B of shape 4, 3, 2. So whenever you do tensor dot, you actually specify the axis along which you want to perform sum reduction. For A, you give this as 1, 0. In this case, that's 4, 3. For B, it's 0, 1. Again, 4, 3. And if you look at the output of np.tensor., the shape is essentially 5, 2. And that's because you have performed the sum reduction along 1, 0 and 0, 1, which means these axes have been collapsed and what remains is 5, 2, which are essentially spread out. If you look at the equivalent code in Python for np.tensor. It can essentially be implemented with 4 different for loops. And in order to exactly understand how this works, please do check out the link that has been given in the notebook. And it's left as an exercise for you guys to try and figure out why these for loops range to particular numbers and why the formula is this way. Hope you found this particular Numpy recitation series useful. Thank you.